Okay, so we're extremely lucky today to have a guest lecture by Sanjivan Chowdhury. There's many things about Sanjivan that are kind of obvious from like a Google search, right? He's one of the world's leading experts in imitation learning. He spent a few years kind of putting all of the sort of theory we've talked about in this course into practice at Aurora. He's currently a professor at Cornell, and before this, he actually did his PhD here at CMU in the Robotics Institute. Um, but perhaps what is less obvious from Google search is just what a gem of a person he is. Between undergrad and my PhD, I actually spent a summer working at Aurora, and Sanjivan was my mentor. And despite the fact I was around the worst intern imaginable, I basically did no work, and my first commit actually broke the whole motion planning stack. Sanjivan still had like a level of faith in me that I still don't have in myself, but I think of many of the successes I've had since then as being in large part due to the amount of belief he had in his students. I would say Sanjivan, I think of him as essentially my third advisor. He's been on every paper I wrote in my PhD, and I've learned so much from him, both on a technical level and just about the sort of person and mentor I want to be. So believe me when I say we're very lucky to have Sanjivan here today, so at least virtually. So thank you, Sanjivan. Please take it away.
Oh, wow. I don't know how to follow that. All right. Hi, good morning, everyone. I'm Sanjivan. I really wish I could be there in person to give this course, but I have to make do with watching tiny versions of you from behind you somehow. So, but yeah, Gokul, thank you for that much too generous introduction. I think it, I guess this, I was taking a look at the course last night and it looks so cool. I feel very jealous of y'all. I wish when I was a grad student, I had a course like this that kind of puts together, it's so interesting. It helps you build a unified framework for how to think about interactive learning, which is at the heart of so many interesting questions. So I think this is an awesome course. I'm going to try to steal this at Cornell if possible. Um, Okay, so today I'm going to talk a little bit about, I'm going to give a lecture or a class that is very complementary to the courses you've had, the classes you've had up until now, right? You've been seeing this very pretty picture of interactive learning that Gokul, Stephen, and Drew have been talking about, and sort of connecting that to, imitation learning, reinforcement learning, and so on. I'm going to give you a glimpse of how all of this translates when you try to go to the real world and try to apply this in different applications, right? So first, a little bit about myself. So as Gokul mentioned, I'm an assistant professor at Cornell. My lab is called Portal. And at Portal, we work on home robot apprentices. So the idea is, how do we get robots to help your grandma cook recipes in your home? We're not quite there yet. We'll have to do with grandma being my grad student, Yuki, and, robots being these two clunky robots working in our lab. But I think we've been making a lot of progress towards this problem. So that's sort of one part of what I do. I also am a part-time research scientist at Aurora. I joined Aurora when it was in its early startup days, and it's been really cool to see it grow all the way from about to do a commercial launch. I guess in the next month or so. So that's been an awesome journey. So that's sort of another part of what I do. And of late, I've been personally very interested in the space of interactive LLM agents. It's taking all the principles, of decision making that's been around for decades, but applying it with this really interesting policy class, which is these language models that reason and then take decisions in the real world. And so that's they're both interpretable, capable, but they also make new and interesting mistakes, right? And so my work is kind of spread across all three domains, and they may look very different when you look at them in one glance. What unifies all of these domains is they're all about interactive learning. At heart, they're about how robots, agents interact with the world, interact with the user, do that efficiently. So everything that you're learning in this course is actually super essential, and it'll help you think from very first principles in a very clean way about any of these problems. Okay, so the goal today is maybe to take a couple of these applications and go a little bit deeper and try to see what are interesting problems in each of these domains. Okay, but first, question: what's with the minion? I've been asked to explain why the minion appeared. So I'm guilty for the minion appearing. I think you might have seen this in Drew's slides. I think the origin story is I was giving a talk at some high school, and I used the minions to explain to convey some emotions, and somehow that got out of control. Made it to my undergrad slides, my grad slides, took over my lab, and now it's everywhere. So excuse the minions. That they're just a way of for me to convey my emotions. All right. So back to the question. You might wonder, why do we need imitation learning at all? Right? By the way, this in the spirit of this course, you know, let's try to keep this interactive. If you have any questions, just feel free to interrupt me. I may not be able to see you, but just shout out your questions or raise your hand, and it'll be awesome. I think this lecture will be much more interesting if we have a back and forth, rather than me going on and on, right? So yeah, please feel free to interrupt. Okay. So back to this question. So why do we need imitation learning at all, right? You might look at these applications and say, can't I just write down a reward function to express whatever I want these agents or systems to do, and then use my favorite reinforcement learning, PPO, to solve this problem, right? And I'm going to try to convince you that that's not generally a good idea. And in fact, there's a fundamental reason for why you want to think about imitation learning or interactive learning. Why this problem is much more fundamental in all of these applications, right? So the first major reason is the alignment problem. So this is what the cool kids call it these days, but I always thought of this as as an imitation learning problem. So let's say you've just got your home robot. It's the latest humanoid from some company, and you want it to do a task in your home, right? You want it to make you a cup of coffee, okay? So, being a good machine learning engineer might sit and design some really nice reward functions for how to make you a cup of coffee. And then you click optimize, and you expect the system to just, make you that perfect cup of coffee in the morning. You do this, and you see that your robot, in fact, burns down the house, right? So what happened? So while you wrote down the reward function to make a cup of coffee, you didn't bother to specify that, hey, don't burn down the house, don't steal the neighbor's coffee, don't make a mess, right? Um, there's all these kind of things that you might think of as common sense, or it's implicit in your mind, that you just didn't bother to specify. And you took it for granted that the robot has a shared set of values as you. And of course it doesn't, right? The robot's just trying to game cost reward function you write down. And so it tries to make you an optimal cup of coffee, trading off every other term, right? So that's, what about in the self-driving setting, right? How does imitation learning show up when we are trying to kind of program a self-driving truck to drive on the road? So this is actually this is actually an old video. This is one of the first intervention-free runs that I went on when I was on the truck. Our system's way much better now, but it's still cool to see the system being able to drive alongside other human drivers, do courtesy lane change, very polite, and essentially drive without any human intervention, right? So how can we get behaviors like this from our robot? You might be tempted to think, okay, if I want my robot to drive like an ideal citizen, I might just, take the official driving handbook, program in the various rules of driving, and then ask it to go optimize those rules, right? And you're certainly welcome to try that, but that wouldn't work in a scenario like this, right? So this organized chaos that we see here is what we call traffic back at home. It's if I look at this video, it's completely unclear to me how I might write down a set of rules to describe what is acceptable driving here, right? Um, somehow, we struggle to write down these rules, but if you're, one of the, billions of people in India, you somehow know these rules implicitly, right? Like it's something you've grown up seeing, you kind of know these shared set of contracts, right? Like, for example, those yellow things that we call autos have right of way over pedestrians. So it's like autos, pedestrians, and then cars. So you wouldn't know that unless you were like you've driven on these roads as much as I have, right? So, anyways, the point that I'm trying to make is that many of these behaviors that okay, also we don't have to go to India to kind of see these phenomenons. If you see something like gridlock, right, where the other cars have the right of way, but because it's gridlocked, you can and should take a left turn, right? And you would be holding up traffic if you don't. These are things that are notoriously difficult to hand design. If it can get very unwieldy if you're trying to hand design rewards to elicit these behaviors. Okay, so the kind of the moral of the story here is that they are explicitly trying to program rewards to express behaviors is not only tedious, it's error prone, and ultimately it's hackable, right? Instead, we would like our robots to be able to infer these rewards from natural human feedback. And that's sort of one of the most fundamental reasons why imitation learning is a very important framework to adopt, right? So in a nutshell, the alignment problem is we have a human and we have a robot. The human has some ideal behavior in their mind that they can, they know it when they see it, kind of a thing. But it's very hard for them to explicitly define that function. The robot is trying to infer a reward function to express that behavior. The human can only communicate to this behavior to the robot through natural modes. So that could be, the most natural thing we can think of is language, right? The human literally says, here's what, make me a cup of coffee. But it could also be through other kinds of feedback. For example, the human demonstrates how to make a cup of coffee, or intervenes when you do something wrong, or shows you preferences between two things, and so on. And the robot, in turn, is actively querying the human to get more information, right? And so this kind of interaction between the human and robot is fundamental in every single application. Otherwise, you would have systems that are not aligned, that are going rogue, that are not doing ideal behavior, right? Okay, so that's the alignment problem. I'm going to pause for questions. Right, let's keep going. So that's the alignment problem. The second reason, which is less common, but it's at the heart of what we do in our lab, is the collaboration problem, right? So if you look at videos of robots out there today, you would notice one thing is that there's no human in the scenario, right? It's just the robot on its own doing stuff. I don't know about you, but I don't want robots driving me out of my homes, right? And so when we built Portal from the very beginning, we wanted to put a human in the environment right from the get-go. I think that was very important to us. So this is a system that we kind of built at the end of our first year at Portal to kind of show what we are trying to build towards. So we call the system Mosaic. It's a modular system for interactive cooking. The idea is you have a human user and you have a team of multiple robots that are helping the user cook a recipe. Now the recipe is kind of in the user's mind. It's not explicitly known to the robots ahead of time. And there are lots of personalizations in the recipes, different ways of cooking, different condiments they might use, different orders in which they might do the task. And the robots are just trying to help the human achieve this, right? So the robots are trying to figure out what tasks they can do that the human just wouldn't want to do, it's too boring, and let the human do the task that feels creative, that feels interesting, right? This is sort of the vision that we have of how we would like our systems to work. Underneath the hood, our system uses a combination of different foundation models to interact with the human, to do manipulation, to grab objects in the world. There's no motion capture. These robots are all using onboard cameras to do these tasks. So here's how the system looks. Sorry, there's no audio in this video, but essentially the user is talking to the system in using natural language. So here, the user prefers to do things like maybe chopping the vegetables and doesn't want to do tasks like having to stir the pot or having to go fetch condiments. And one of the things you notice is how closely intertwined the human is with the robot, right? So the robot here is looking at the human through cameras and kind of predicting their intent, right? Predicting, when they might come close, when they might need some space, when they might want things taken over, and acting accordingly. So each of the policies here is very closely collaborating and interacting with the human, right? Cool. So the collaboration problem is as follows, right? You have a robot that is interacting in a world where there are humans in that world, right? That means, we can't have robots taking random actions because, that would freak the human out, right? This is not tabletop manipulation where the robot just tries out a bunch of actions and hopes for the best. The robot has to be very judicious with interactions that it does, right? So interactions need to be safe, they need to be efficient. And so doing reinforcement learning with such an environment is just off the table, right from the get-go. You can't just do exploration with the human in the loop. You have to be able to bootstrap off of maybe good human-human interaction data that you may have. And so some of the intent prediction stuff that I showed you in the previous video, we actually train that by capturing human-human interaction data, training models of how humans should interact, and then transferring that to human-robot interactions. So the alignment, so this is the collaboration problem, right? Robots live in a world with humans in it, and so you kind of, the human is a first-class citizen. The robots have to be able to interact efficiently with humans, and imitation learning gives you a good framework to kind of gives you a good prior to start off of. All right. Okay, so hopefully you're motivated by now that we need imitation learning in these real-world applications. We can't just do RL. And the next natural question is, why is it challenging to do imitation learning, right? And that's sort of what we're going to explore today, right? The key challenge, there are many things that make imitation learning challenging when you start to actually apply it in the real world, but we're going to zero in on the challenge of trying to make interactions efficient. So you have this robot in the middle. On the one hand, it's interacting with the human user to figure out, what reward function they have in their mind. On the other hand, it's interacting with the real world that may have humans in it. And both of these interactions need to be as efficient as possible so that the robot can do the task, right? And so that is really the key challenge when you're trying to deal with real-world applications, okay? And today we're going to take a look at each of these challenges one by one. All right, so I'm going to tell this through the lens of two very different applications. One is self-driving, the other is dexterous manipulation. I tried to make this lecture so that you don't need any background in any of these applications or robotics to follow what I'm doing. So if at any point something doesn't make sense, just interrupt me and I'll try to explain as best as possible. My hope is you're able to come out of this lecture just having some idea of how these things make their way into real-world applications and maybe engaging with it, okay? All right, so let's begin with the first interactions, the one with the robot and the human, right? And I'm going to tell this story through the lens of self-driving. Okay, So I'm going to talk, maybe the best way to start this story is to talk about the first self-driving car that I worked on. And no, it was not at Aurora. And it was not a full self-driving truck. It's in fact these really cute little RC cars. Back when I was a postdoc at University of Washington, one of the first things I did was team up with a bunch of really excited undergrads to build these RC cars as like an open source robotics project. So these cars are essentially 1/10 RC's cars with a cheap lidar on top with an RGBD sensor in the front. The hardware for these cars, we made everything completely open source, the hardware and the software. We've had a number of people actually be able to 3D print and assemble these cars. And so it's been used in different places to teach courses or just as a fun experiment bed. It's really cool. We have like 20 of these cars at Cornell that are used by different undergrads. So it's really, the goal was to get this very, very easy to use test bed to be able to do machine learning research essentially, and apply it as easily as possible to a mobile platform, right? Okay, so one of the first things we did with this car is we wanted to teach it how to drive, right? And being good imitation learning students, we wanted to teach it how to drive via demonstrations. We didn't just want to program in rewards, that's boring. Let's get a human to drive around the cars, and these cars can go really fast. So our goal was to get it to go very, very fast. We never achieved that goal, but that was the North Star. And so here's Jonathan. Who's one of the first guinea pigs to drive around these cars. He got very good at it by the end. So Jonathan here is teleoping the cars through the corridors and recording demonstrations. And now let's really talk about, get to the nuts and bolts of how do we train a policy. So what does my data look like? So the figure on the bottom right gives you a glimpse of how the robot sees the world, right? So those black and gray lines is what we call an occupancy map in robotics. It's basically, think of it as like a 2D image, an overhead image that tells the robot what is free, what is occupied. You can get fancy and semantically annotate what is corridors, what's an elevator, and so on. But for now, let's keep it very, very simple. This is a binary image telling you what's obstacle, what's not. Your data looks like a sequence of states and actions. So states are 2D coordinates in this map. Actions are you can think of actions as joystick commands that the human showed. The way we to kind of reduce this problem to our favorite classification problem, we selected a very simple policy class, which is a trajectory library, right? So you have a this beautiful blue and red color that you see. These are the various trajectories. And think of these as discrete tokens or discrete actions that the robot can take. We took the human teleop data and we sort of projected it to one of these discrete actions that closely matched what the human was trying to show. And then you do behavior cloning. So you've learned behavior cloning in this class. So, we just applied standard vanilla behavior cloning. We did due diligence as machine learning engineers, made sure training error was low, made sure validation error was low. We ended up with a policy that even looked reasonable. So the colors show you what is blue is good and red is bad. And the policy looks pretty reasonable, which is try to go around the corner as quickly as possible. Crashing into obstacle looks bad. One of the interesting things you see is it's not perfect. So the error is not 0, it's epsilon. So it does tend to like some of those trajectories that graze the edge of the wall a little bit, but most of the probability mass is on the right trajectory. So we called it a day. It's like, this looks good, let's deploy it. All right. So how does this do when you deploy it? Looks good, looks good, looks good, boom, crashes. All right. So it was driving perfectly well. And then suddenly, just when the corner was coming up, it sort of took a premature right turn. And once it started to take a right turn and head towards the wall, it just, it just didn't bother to correct, just kept going, right? So what do you think happened here?
It could not recover from a catastrophic error. So the human demonstration must not have had this state. So yeah, it just did not know.
Wow, preaching to the choir. Okay, great. Awesome. Yeah, exactly correct. Right. So this is what the demonstrations looked like. Like they looked ideal. They looked perfect. Very nicely cornering. Now as I said, our policy isn't perfect, right? It has some error epsilon. So it's only natural for it to make a tiny deviation and go off. Now, once it goes off and it's now pointed at the wall, it sees very little or almost no training data. And at that point of time, the policy can act arbitrary. Now you might ask, okay, if it's acting arbitrary, does it have some probability of recovering? I mean, turns out in practice, the most common data point it's seen is to just drive straight, right? Most 99% of human driving is just drive straight. So it's just defaulting to I'm just going to drive straight. So it just keeps going straight into the wall and then crash. Okay. Great. All right. So that's not great. How do we fix this problem? I mean, just to make the point even more crisp, if we did a due diligence and looked at training and validation law. So you might ask, okay, was validation error very high? No, our validation error was very low because we measured it on the distribution of states at the human visits, which is mismatched from the distribution of states at the robot visits, right, at test time. Okay, great. Now can we go back to the question? How can we avoid this compounding error? What algorithm have you learned in this course that you might apply to take care of this problem?
Dagger?
Dagger, yes, thank you. Awesome. This is like super easy to teach. Okay, great. Dagger. So let's go through the Dagger loop. We take our policy, we roll it out in the world, we collect expert actions on all the robot states, we aggregate data, we update the policy and repeat, and you may or may not have gone through the theory that shows you how this goes from O epsilon t squared to epsilon t. Gokul's told you all sorts of wonderful things about it. So that's it. This fixes our problem, right? We can just apply Dagger and go home, right? What's the big deal? What do you think happens? What do you think is a challenge if you try to apply Dagger to this problem? Practical challenge, not a theoretical challenge.
Jonathan gets tired.
Jonathan gets tired. Jonathan gets very cranky, not just tired. Jonathan threatens to quit the project. So needs a lot of consoling afterwards. Yeah, because I had to make him implement the baseline too. But anyways, it's really impractical for him to sit and provide feedback data everywhere, right? It's too much human effort. And even beyond getting tired, it's actually unsafe. I mean, one of the analogies I like to think about is, imagine you're a driving instructor, right? And you're teaching a really, really terrible student how to drive, right? And in fact, that student is driving on the other side of the highway and then hands you back the control and be like, hey, what would you do? I mean, you're already freaking out. I think that is not an ideal position to be in, and you don't want to be in a self-driving truck and trying to do Dagger on it. That would not go very well. So it's super impractical to query this expert everywhere. Can we think of more natural ways? I mean, how do human drivers learn? I mean, you don't learn from all feedbacks. I mean, naturally we your driving instructor just intervenes when you do something stupid and then corrects and then gives you back control, right? It's a very natural way in which humans like to teach, and we want our robots to be able to learn from this, right? Okay, so how do we learn from interventions, right? Can we kind of try to take the principles from Dagger but apply it in this kind of setting. So the setting is as follows. You have a robot. If the robot's doing fine, good enough behavior, the human is hands-free, they're not giving any corrections, not bothering to correct. Anytime the robot does something bad, the human kind of intervenes, takes over, and drives back, right? Okay, yeah. So that's kind of the model. Instead of giving feedback every single state, the human is only giving you feedback when you're doing something bad or you've already done something bad, and then they recover, right? So they're never actually giving you feedback on all the nominal states. They're never giving you feedback on the dangerous, irrecoverable states, right? So a natural way to adapt Dagger to this setting, you might think, is essentially to only keep the expert actions when the expert intervened, right? So keep the exact Dagger algorithm as is, make no changes, but only keep the labels where the expert intervened. So instead of querying the expert at all states the robot visits, just keep the labels where the expert intervened. That seems like the most straightforward application, and there's even a paper on it called HG Dagger that does exactly this, right? Okay, so the algorithm is roll out a learn policy, collect expert actions on states with the expert intervene, aggregate the data, update the policy, repeat. Now, does this work, right? Seems obvious. Can we see, let's take a look at this algorithm and maybe, can you see things that might go wrong with it, like counter examples to when this might not do as well? Okay, so let's think a little bit more, right? Let's take the same example of the robot driving around in the corridors, right? And you're only keeping the intervention data around in Dagger, right? And maybe you're doing really good in imitating all of those intervention actions, right? So you're doing a good job of, so you're running this Dagger loop. At every iteration, you're getting intervention data, and you're doing a very good job of imitating those intervention actions perfectly, right? Would you have a good policy? Are you guaranteed to have a perfect policy that doesn't result in more interventions?
I guess would you spend less time in the nominal states, like the more ideal blue region?
Yeah, exactly, right? So as this is going on, your data mix is changing. It started from good nominal data, and now you're getting more and more intervention data, all right? And as a result, so one of the first practical things that happen is your nominal data distribution is going down. Your data mix on which you're training looks like a lot of intervention data. You're getting really good at knowing how to recover when you've done a bad thing, right? But the policy that achieves zero loss or very low loss on this aggregated data, is that policy guaranteed to not make the mistake in the first place? No, right? There's no signal that you're giving to the robot that says, hey, don't do this bad thing, right? You're only telling the robot, recover when you've done this bad thing, but you're never telling it, don't do this bad thing in the first place. So you might end up with a policy that has really low loss according to this algorithm, but that policy looks like this, drunkard kind of a robot that, makes does poor on nominal driving, but then is just really good at intervening. So it just swerves towards the wall and then turns away, right? And you get this kind of very wayward looking trajectory, which is not what you want, right? You don't want the robot to be making mistakes in the first place. Okay, so one of the key things that this idea misses is that interventions are actually giving you some information about the expert's latent value function, right? They aren't just telling you, here's how to recover when you've done something bad, but they're actually giving you information about what is good and what is bad, right? And if you're only if you're only trying to imitate the recovery actions, you are leaving this information on the table, right? So that sort of was one of the key insights behind our work. So we call this work expert intervention learning, or EIL. The idea was very simple. The expert has some Q function in their mind. Let's call it Q star SA. This Q function is latent. We can't see it, but we can try to guess some constraints or some properties about the Q from the interventions. Okay. So the idea is interventions are giving us some information about this latent Q function, right? So let's think of this a little bit formally. So let's say our goal is to learn a good Q function that's able to minimizes some loss on nominal driving data, right? Like a good Q function should explain nominal human demonstration data. But now when the expert is not intervening, right? We can make some assumption about the Q function. So by the way, here the Q is one of the problems with roboticists is we think in space of costs rather than rewards. This is because some of us are control theorists. And so you get this absolute mess with notations and signs. I apologize. Here, low Q is good because it's sum of costs. Usually in RL, high Q is good. So here we had the cost formulation. So we want to have small Q values. Anyway, so when the expert is not intervening, we can make some assumption that, okay, the Q value is actually pretty good. So it's below some threshold delta. The actual value of delta doesn't matter. It's just for explanation purposes, right? So the Q value is below some level set. When something bad happens, when the expert intervenes, we can then say that the Q value is actually higher than this threshold, right? There's a difference between the quality of the value of states when the expert doesn't intervene versus when they do intervene. And finally, when they're showing you recovery actions, that recovery is better than any other alternatives, right? So these three properties give you a way to express constraints on various Q functions, right? And you can plug this into your favorite online convex optimization and get out a Q function from the stream of intervention data, right? So the algorithm looks very much like Dagger, right? Except at every iteration, we take the intervention data, we back out these constraints on the Q function that you can think of that as the policy, which is just parameterized as a Q function. And then you solve for the policy that has minimum loss, and then roll that out, collect more intervention data, and so on. The key difference between the HG Dagger and here is you're actually trying to constrain the policy you're actually trying to express this constraint that some states are worse than other states, and so you should not go to those bad states. You're expecting that a policy over time doesn't actually breach this bubble of good enough driving. All right, so how does this work in practice? So here's how Jonathan is intervening. So the robot's control, when it's about to get close to the wall, he takes over, hands back control to the robot, gets close to the wall, he takes over. And this is how EIL works. So the first few iterations is just like behavior cloning. It knocks into the wall. After 6 iterations, it's doing this drunkard walk. But after 12 iterations, it's able to drive really nicely. Performance that was all we really needed for I was able to go round and round the corridors pretty much without colliding. And even if we double the number of demonstrations in behavior cloning, it still fails because we are just simply not seeing that recovery data. Kind of just to show you some quantitative numbers of how the performance looks with expert queries. So the thing we really care about is being very query efficient, minimizing the tax on the human for providing feedback, right? So on the x-axis is expert queries. How many samples did the expert have to provide? So the yellow line is behavior cloning, right? So behavior cloning, even though you give it a lot more and more expert data, and the expert is a little bit suboptimal, so it's showing you some recovery data, but not a lot. You behavior cloning gets better, so the error goes down, but it's kind of asymptoting at a high point, right? Because it's simply not seeing this recovery data. Dagger goes, yes, this was the thing that was very painful for Jonathan to implement, but Dagger does go down. But Dagger is querying the human in a lot of states that are, nominal, where the robot kind of gets it right. And so you're wasting your precious query budget on states you don't really need feedback on. So that's the green curve. HE Dagger is good. So it's more efficient. It's just keeping out on the intervention data. But on one of the data sets on the left-hand side, we start to see AG Dagger kind of not be able to correct as fast because it's not using this implicit information that good states, not intervention is good. And then finally, EEL is the dark line that's kind of able to squeeze the most juice out of expert queries. So yeah. This is sort of a very simple approach of how you can try to extend something like Dagger and try to make it more query efficient, and make it more practical. Right? Questions before we move on?
So it'll eventually give you back a Q function, a Q estimate,
Yeah, that's right.
and that's different from aggravate.
Yeah, that's a great question. So aggravate would essentially requires that the expert give you Q values. So that could be either they tell you the Q values and you do cost sensitive classification, or more practically, from every state the learner ends up at, the expert finishes the trajectory, and then you compute the cumulative reward or cost on that trajectory, and that gives you your targets, right? So aggravate is almost on the spectrum of efficient to practical to impractical. Is the most impractical algorithm, right? Because it's requiring this kind of very expensive Q labels for every single action. Right? Here, what we're doing is we're not requiring Q labels. We're simply trying to put constraints on the Q function, right? And if you have more information about the Q function, you can just add that in. Like if you happen to know the ground truth rewards, you can just put that in. Like you can put a temporal difference constraint on Q if you happen to know the reward, and get a better estimate of the Q.
So how do you choose the threshold in the constraint?
So it turns out it doesn't actually matter. Like it was just to make this point. All you're showing is you prefer the QSA of your good bucket. You just partition your data into good and bad, and you're saying the good bucket Qs are less than the bad bucket Qs, right? So the threshold actually goes away. It's just it ends up becoming an ordering.
Just comparison feedback.
It's a comparison, yeah, feedback. And actually, we'll talk a little bit about that next in a second, right? Yeah, but that you don't need to care about thresholds. Cool. Awesome. Okay, so great. Now let's go from toy RC cars to real world self-driving. Turns out there's not a lot of work required to scale this up. So once you get it working on an RC car, you're pretty much 80% of the way there. All right. Okay. So now I'm going to show you a bit of jargon, but just to give you a glimpse of how modern self-driving architectures look like. This is not the Aurora architecture. I cannot show you that, unfortunately. I would love to. But this is, from Waymo, but this is kind of representative of how pretty much the current thinking of almost all self-driving problems, which is copy what language modeling people did, right? So a typical self-driving architecture looks like this, right? You're on the left-hand side is what you call a scene encoder. Think of it as I take information about every single car, pedestrian, auto, whatever in the world, um, uh, and also artifacts of your map, like your traffic light, your lane signals, and so on. And you encode them, you embed them, um, using some embedding model to get some embedding of the scene, right? Okay, so that's not super interesting, but you get some embedding of the scene. Then so your policy looks like you want your robot to be able to take driving actions. You can think of driving actions as being like a language modeling problem where your tokens are essentially what um, um, you can think of your tokens as kind of what action you took at every time step. That could be one way to think of your tokens. You can also think of, just for this discussion, you can think of you're predicting only one token, right? Which is, what action should I take at the current time step? I think that's simple enough, right? And so that at a high level, that's sort of how we typically architect the policy. We take your information from the world, embed it in a scene, and then decode that scene to predict what action the robot should take. Okay. And going a little bit more into details, how we train, that's more interesting rather than the model architecture. So, similar to language modeling, you do a lot of pre-training of your scene encoder on all the driving data. So this could be not just the driving data that your company has, but on driving data that you collected from all other cars on the road, because you're trying to build an encoding of the scene that's predictive of how the future might evolve, right? Like how you're trying to forecast how different cars or elements in the road might evolve in the future, and you're pre-training on all of that data. But the decoder that's actually giving you action tokens that your self-driving car will do, that you're fine-tuning on good driving data that you know to be good. Maybe that's data that your good human drivers demonstrated, and you're fine-tuning on that, right? And this is pretty much the playbook for how most of the effort today goes into kind of getting this flywheel working, right? Collecting good driving data, maybe tagging what is good versus bad, cleaning it up, and then it's very easy to scale. Humans are good at driving, or some humans are good at driving, so you just go collect lots of human driving data and then just fine tune this, and this should just work. Okay. But one of the things that not only we but others have seen time and time again is even at self-driving, which is the largest scale of all the robotics applications, nothing has seen scale or money or time as much as self-driving has, right? So there's a lot of interesting lessons to be learned from self-driving, right? That's predictive of the future. So one of the things I learned from self-driving is it's just simply scaling up human demonstrations is insufficient, right? And fundamentally because demonstrations don't tell you what not to do, right? They just tell you what is good driving, but they don't tell you what is bad driving, right? In some sense, there is a lot of invariances when you're driving. The human might have, let's say you're driving down the road and there's an empty lane, and the human lane changes at a particular time, right? You could have lane changed at any other time, and that's totally fine, right? But the demonstration is not showing you that invariance, unless you collect astronomical amounts of lane change data, which we just don't have, right? But we know that invariance exists, but we are just not communicating that to the system. So demonstration don't tell you what not to do. Demonstration also don't show you how to recover from bad scenarios, right? like, the human doesn't get into the bad scenarios, but the robot gets into all sorts of, tight spaces, bad merges, and the demonstrations simply don't cover those scenarios. And those are often the scenarios that we are spending a lot of effort trying to make the system better. This is this long tail of self-driving that seems, just impossible to conquer, right? And demonstrations are not helping you in this regime. Okay. So this is common knowledge right now. How can what we learned about interventions help in this scenario, right? So I'm going to talk about, so we looked at this very kind of toy setting of intervention. I'm going to talk about how this works for real. So, you know, let's say we have an on-road event, right? So in this case, this is, for 5 years ago, but it's still cool. So we have this kind of on-road event where, let me remember what the scenario is. Right. Okay. So here the car is taking a right turn, and there's this kind of vehicle that begins to park, right? Now the car can't infer that the vehicle is actually parking. It thinks that, the vehicle's just stopping, right? So the car incorrectly brakes in the middle of, flowing traffic. And so you have the AV operator intervene, take over, and safely nudge around the vehicle, right? So that's a typical on-road. You can think of this as an intervention event. You have a team of triage people who are able to quickly tag this intervention event and do some annotation on it. And the annotation ends up looking like a unit test, right? The unit test looks like, this is good behavior, this is bad behavior. So it becomes a sort of a test that is much more durable, on which every time you train a new model, you can actually check the model against that test. You can just think of this as another way of constraining the Q function that you might be training, right? And so you iterate, and then update your model, deploy it in the real world, and hope that so in this case, the nudging, after using enough number of these tests, the nudging behavior actually got really good, where it was able to infer when it should nudge around stop vehicles and when it should wait for vehicles to go, right? Which can get in congested streets, this can get very, very tricky. This is especially streets around Lawrenceville, which is an absolute nightmare. My God. Anyways, it was those were like our hard cases where this tend to work really well. Cool. So this is how simple ideas can be scaled, right? One of the lessons that I learned from this project is you don't want to just because an idea. I guess if you're thinking about the utility function of ideas that can be scaled, it has to be an idea that's simple enough that engineers can replicate it, that replicate it poorly and it still sort of works, and it's easy to explain, it's easy to verify, but it's grounded in some theory, some principles that we understand, right? I think the combination of this two is the sweet spot, and some of this intervention work and the insights actually kind of hit that sweet spot really well. Okay, just to kind of complete the story, how do we think of interventions now in the system we have today? The nice way to think about interventions is as an automatic preference generation, right? So every time we do an intervention, we get at least 2 data points. One of the data points is saying we prefer not to enter the intervention state, right? So the trajectory that led to the intervention is a rejected trajectory. And you ask, human annotators in this case to give you a chosen trajectory that would have avoided that state. So that's one preference data. The second preference data is once you did intervention, right? The recovery that was shown was optimal, and whatever the robot was doing was rejected, right? So you're getting this automatic preference data that's just populating from any on-road interventions into your system. And most pipelines today look a lot as follows, right? You have your demonstration data that's being used to update your SFT policy, and then you have your interventions data that's giving you automatic preference data from which you're training reward functions that you're then using to kind of fine-tune this policy to not make those errors anymore, right? Do some kind of preference fine tuning or to do some kind of RLHF, right? So the details here, depend on what infrastructure you have, but the general principle of turning interventions to preferences is pretty nice. Yeah, so and it's something that roughly works in the real world. So okay, I'm gonna stop here for the first part. Let's see how we're on time. Okay, guess we got 20 minutes left.
Yes.
Okay, cool. Anyways, questions on this, everything we covered up until now. No? All right. Sounds good. Let's go on. Let's pick up the pace. So we talked about this, we looked at a method of kind of learning from human interventions and being query efficient. Now let's look at the other half of the story of how do we be efficient when we're interacting with the real world. And I'm going to tell this story through the lens of dexterous manipulation. So we're going to switch gears completely. And this has been a field that, it's a fairly fast evolving field. There's a lot of interest, multiple companies working on this. The first thing I should say is if you're not into robotics, it's pretty impressive what robots can do today. Like we've made a lot of progress in the last few years. This is a video from one of the cool new startups called Physical Intelligence. This is their first policy Pi 0. And the idea is, this policy has been trained from bioimitation learning. And it's doing all sorts of dexterous manipulation tasks like folding your laundry. And these demos look really super interesting, and these are traditionally tasks that roboticists thought were really hard, deformable manipulation. You had complicated, unwieldy methods to do it. It turns out the solution was, as simple as collect demonstration data, use behavior cloning, and that gets you a long way. Now, by no means these policies are perfect. Like their success rate is around 60% or whatever. But so nothing close to a product, but progress, right? Great. So how do we train these robot policies today? Okay. So what changed? What made robot learning cool again? One of the things that made all of this possible is actually being able to scale up demonstration data, right? And a lot of that has come with the rise of teleop interfaces that allow human robotics engineers to be able to provide demonstrations maybe easier than it was before, right? And so these are these haptic interfaces. This is the video that you're looking at is called Aloha. It's one of the many interfaces that are around. These interfaces typically look like, it's not as easy as it looks. It's actually very difficult to get these to work. But you spend enough money, train a person to work with these controllers, and then they can start giving you teleoperation data fairly easily. There's lots of different options in the market, right? So one of my favorite ones that we played around in the lab is this interface called UMI. So this doesn't require any fancy teleop. It's like a cheap thing that you can 3D print. We 3D printed. And you as a human can give kind of very natural looking demonstrations. You don't even need to control a robot. You're simply just controlling the hands of the robot. And these kind of interfaces record important sensor measurements like camera, and some of them record force-shock sensor, and that gives you demonstration data that your robot can then go and imitate, right? Because most of these robot manipulators are really trying to get the wrist motion, the end effector motions correct. Okay, so we can now scale up data, which is great. Model. It's still doing behavior cloning at the end of the day. After all the bashing you did of behavior cloning, it's still behavior cloning. But well, I guess what changes powerful BC policies, right? So typically what BC policies for manipulation looks like is you have an observation OT, feeds it into a model, your policy model, and it outputs an action AT, right? And now this action here is a 1 to 2 second prediction of what the robot should do in the future, how it should move its end effector, right? So that's your policy. Underneath the hood, these policies are typically visuomotor policies, so they're operating on vision alone or vision and proprioception. So they're taking the image, this kind of third-person image of the robot, pushing it through your favorite, image encoder model, Resonant 18, Dino, whatever, V2, and giving you an embedding vector that you're decoding to predict the action. That's basically it, right? So what's challenging about this problem, right? Why is this hard problem? One of the challenge with controlling robots is that the output space is high, it's continuous, right? It's continuous space of actions, continuous space of sequences. It's high dimensional, but it's multimodal, right? So take this example of manipulating this T to get it into the right shape, right? There's a number of places you could move your end effector to kind of get it to reach this target space. And in fact, your data might contain demonstrations doing different things. Now, quick question. What happens if you do behavior cloning with a model using L2 loss and with a model that's just giving you a single trajectory as output? What do you think would happen?
Since it takes an average trajectory, I mean, it follows the wrong path.
Exactly. It's going to take an average of all this motion, right? And that's just comes from, I don't know if we covered distribution matching, but it just comes from the property of KL divergence. And if you try to fit a unimodal Gaussian to a multimodal model using forward KL, it's just going to try to spread the variance out to cover all the modes, and the mean is just going to be in the middle, and that's going to be wrong. In fact, the mean might have 0 probability on it, but or very little probability on it. And so, yeah, this would just average over all the trajectories. Not good. So how do we, what class of models allow us to model such complex distribution spaces, right? Multimodal over continuous actions. And one of the things that became popular over the last several years or last few years rather, is diffusion models. So I'm not going to go into details. It's not relevant for this talk, but at a high level, you can think of, instead of trying to model this this complex multimodal probability distribution, you are instead trying to estimate the score function or the gradient of this probability distribution with respect to x, which is much more easier to estimate. And then, so you're trying to estimate the simpler function that then you, at inference time, you are going to, maybe sampling from it is a little less straightforward, but it allows you to still sample from this complex interactable distribution. Quite simply put, the way you train this model is you take images of or take the output that you want. In this case, cute puppies. You noise it using a forward process, and then you train a model to reverse the noise, right? Okay, so the state-of-the-art method in robotics today pretty much takes this idea and applies it to a robot. So the idea is, instead of denoising pictures of cute puppies, you're denoising the trajectory the robot should take, right? But the basic idea remains the same, right? And so this allows you to, handle multimodal data by fitting in any one of the modes instead of trying to average over the different modes, right? And turns out that this kind of, you can think of this as a much more powerful BC class that now allows you to drive down error much lower than you could before, right? Okay, I am not going to talk about this. It's just too complicated. Okay, so this is kind of diffusion policies in action. It works really well. Like I should first say, like it's surprising how much mileage people have squeezed out of behavior cloning, right? To the point where you might question, why do we need anything else? This looks awesome. I can just scale this all day. I'm pouring pizza sauce, I'm doing cups. It's caused me and Gokul to have many late night existential discussions. Why we're doing research? What's the point? So yes, so I'm not gonna I'm not gonna get defensive and say this won't work today, but it's surprising how well it can work, and a lot of projects in my group actually use this, and I'm always surprised at what it can do. However, before I go on, essentially, and this is sort of the playbook that many the companies like Pi0 are following, where you're replacing your fancy image encoder with you put language in it, you can put multiple images in it, you can take your greatest, latest VLM model, whatever, take the embedding layer and decode it to get the action. So you can make your models more and more powerful. You can make BC more and more powerful, and essentially the story of robotics is scale up to teleop, scale up models, and sit back and profit, right? Don't need to apply your brains anymore. And so we don't know if the story would work or not. We just we don't have enough evidence to say yes or no, right? I think the practical evidence I can say is, if this were that simple, self-driving, this is what we would be doing in self-driving. We actually have a lot of teleop data, and we have a lot of money, and we can scale up the models, and it hasn't worked. So that's one evidence against the story working. It's just that robot manipulation hasn't reached that point yet. They're happy with 60% success rate, right? So one problem with the story, this is just taking the lessons we learned from self-driving, is that at the end of the day, no matter how you collect demonstrations, they won't show you how to recover from mistakes. So that's sort of one phenomenon. And that the second, robots will always make mistakes, right? Because if for no other reason, partial observability, right? Robots do not have the same context as humans. They don't have the same senses as humans, right? The humans giving demonstrations. So inevitably, the human will see something, know something that allowed them to give the demonstration, but the robot can't see it, right? Like, you just think about, the human knew that there was an item in a drawer, and the robot didn't know there was an item in a drawer, right? Even with perfect senses. And so the robot might take an action that the human didn't take, right? As soon as it takes an action the human didn't take, if it doesn't have demonstration data, you are not going to see recovery. You can have this wishful thinking that your model will extrapolate and will generalize, but that's wishful thinking, right? When it actually doesn't, I think, you don't have a lot of answers if you just adopt this scale-up demonstration story. So we need some more options in the menu eventually, or some tools in our arsenal to deal with this. And so, Gokul talked about inverse reinforcement learning. I actually think this is going to be the most important tool to deal with this problem. And the idea being that, robots, it's unreasonable for humans to tell robots how to learn, how to recover. Robots have to interact with the environments to learn how to recover. That's the basic idea of IRL, or how it's separate from behavior cloning. Okay, so let's try to actually see apply IRL in the last 5 minutes and see how what challenges we might face, right? So we have some demonstration data from humans. Okay, we use that to train a policy. Let's call this a generator, right? So we have a good initial policy. We roll that out in the real world. Oops. Okay, roll that out in the real world. It does something. Maybe it does something not good. We collect the data of not good actions where it completely missed the T, and collect data of good actions, what the human showed, and feed that into a reward model. Think of that as a discriminator. The cool kids call it a verifier, whatever, right? So the reward model is trying to say, okay, human good, robot bad, right? It's trying to discriminate between human and robot. And then that reward model is being optimized by the policy, right? So that's the basic IRL framework in a nutshell. Okay. So the idea is, I guess you talked about this in the previous class, you want to train your policy to be able to do as well as a human on any class of rewards that your reward model picks, right? And so here, your reward model here is very simple. It's taking the image and mapping it to a scalar reward. It's solving a very simple classification task of human versus robot. And your policy, pick your favorite RL approach that you're running to improve your policy, right? And you're playing this game between a policy and a reward. Okay, great. What's challenging? Why is this hard? Why is this hard?
The reward model.
Reward model. Say more.
I mean, it's probably difficult to get a good reward model train a good reward model. Yeah.
See, there are definitely challenges with training reward models. But let's say for the sake of this discussion, your reward model is decent. Are there any other challenges you see to doing this, applying IRL in the real world?
The Earth is a dangerous place.
Yeah, right. The world is a dangerous place. Very wise, Stephen. Right. And and you don't want, your policy is like your baby, right? It's like you don't want your baby to go, I have a 7-month-old and she's gotten to a point where she's grabbing everything right now. And if I take her eye off her, she's just gonna grab she's exploring the world, and I don't want her to explore and hurt herself, right? And so your robot is like your baby, right? If your robot starts like flinging around in the real world trying to recover, to figure out a good policy, that's going to take a lot of sample, a lot of interaction with the real world. B, it's going to be very unsafe. Your robot's going to, you're going to break your motors. You're going to have to fix it. Your grad students are going to quit. So like, it's not a good idea to do this. So this is one of the big impediments for why people, IRL is beautiful in theory, but in practice, it's just brutal to get this working. But there's no other way. Demonstrations are not going to get there, right? So Gokul and I found ourselves like, we have to do this. We have to solve this problem somehow, right? And so one thing that robotics that has been that came to the rescue is this notion of world models, right? This idea of let's model the world so that we can it's a safe space for us to explore, try out. Models are a safe space for the robot to try out random things, learn good policies, and then carefully deploy it in the real world, see what goes wrong, update our models, and continue, right? So models have been every single production robotics model, cool result, has involved a world model, from the OpenAI dactyl hands to some helicopter work I did in a past life to self-driving. Models are everywhere. There are really powerful practical code bases that allow you to learn models end to end from pixels, learn these latent world models from images alone, which is super flexible, right? Because you don't want to sit and have to engineer in constraints. Okay, we're out of time, so I'm just going to stop here. So the idea was very simple. We take this picture and use real world data to learn a world model, then have the robot plan in this world model that it's learning. And then, all of this is going on in the mind of the robot, right? So this interactions with the model is happening in the mind of the robot, and then the policy is taking actions in the real world. So this is kind of the best, most practical framework we have today for getting IRL working in the real world. This has been a long collaboration with Gokul and Arnav, who's a student at Mila. And we've got some really exciting results that I just want to end on. So these are some really challenging real robot benchmarks where your diffusion policies, no matter how many demonstrations you give it, the performance starts to asymptote. But then if you bring in this practical IRL, this model-based IRL, what we call IRL square, you start to see them, do much better with much less demonstration. I'm gonna stop here since we are at time. Yeah. So the kind of the key takeaway today was that, if there's one thing you should leave the room with is that, making these methods practical in the real world, the thing you want to think about is how do you make interactions efficient? And here interactions are with both the humans and the robots, right? And so, hopefully this gives you a bit of, some glimpse in how we make these methods work in the real world, right?
Guess we're at time, but if you guys have questions, feel free to stick around to look at the screen and appreciate Sanjiban's work.
Yeah. Any questions? Yeah, go for it.
Good question.
So how do you actually determine that your world model is good enough to start using it at all?
So is the question is how do I know if the world model is good enough to solve the task, right? That's great. So in practice, the way we can evaluate the goodness of our model, right? Like you can imagine that let's say these are some real robot rollouts. You can imagine evaluating the prediction error of your model and matching that with what reality predicted. That could be a rough approximation of saying, is my robot doing bad because my model is bad or my policy is bad, right? And that's something we do quite often, right? We take a policy that we know is good and we see, is our model predictive of, so, okay, the V0 of that answer is, does my model predictions match what happened in the real world? Now, that's a very harsh criteria because modeling the real world is really, really hard, right? There's lots of noise, lots of stochasticity. The model, may not be able to predict exactly the right future that happened in the real world. So the next thing we want to say is, how good is the model at predicting the success or failure of your policies? Let's say you have a bad policy. Can the model tell you that policy is bad? Or vice versa, if you have a good policy, can the model tell you that's bad? And so that's a much more meaningful comparison of evaluating models. And so that's typically how we can tell whether the model is doing good or not. Yeah, that's a great question though.
During deployment, do you use a discriminator for selecting a good path or something for the trajectory?
Yeah, great question. So in this work, during deployment, we are still using a planner and to take action. So we are doing there is some planning happening at inference time. If there's planning happening at inference time, you need like a reward function so the planner can choose good action. So we need the discriminator and the model at inference time. But one of the variants of this work that we're exploring is to be able to distill down the outputs of the planner back into a policy, right? So essentially, you can treat this planner as an expert and simply do Dagger with this planner as your expert, and then distill that back into diffusion policy. And so you don't need the planner or the discriminator at test time. You're just executing the policy. And if your policy is expressive enough, that should be all you need. So maybe that's like the more practical long-term goal we're going for. But having a planner at inference time is great because the more power you give it, like the more the better the output is. Right?